Welcome to this explainer. Today, we're going to completely demystify the science behind electrical circuits. We'll be taking a really fascinating journey from the microscopic level of atoms all the way up to the massive electrical grid that powers our lives. Let's dive right in.
Before we even get into defining what a circuit actually is, I want you to imagine something for a second. What would happen if the invisible circle that keeps our modern world running just snapped? We tend to take electricity for granted, treating it like the air and the water, but understanding how it flows is absolutely crucial to understanding modern life.
Okay, here's our micro to macro roadmap for today. We'll hit 1. The building blocks of electricity. 2. Static versus current energy. 3. Generating the electric flow. 4. The science of circuits. 5. The giant electric grid. And finally, 6. Powering our daily lives.
Section 1. The building blocks of electricity. To really grasp this massive national infrastructure, we actually have to start incredibly small.
So what is electricity? At its core, it's really just a form of energy that happens when electrons get bumped from one atom to another. Electrons are these tiny, negatively charged particles hanging out inside atoms. And atoms are literally the building blocks of all matter. They're in everything. When those electrons play a microscopic game of bumper cars, jumping from atom to atom, that movement, that flow, is electricity. It's totally natural, and it's even happening inside our own bodies right now.
Section 2. Static versus current energy. Once we've got those electrons moving, we really need to understand how that energy behaves out in the real world. We basically encounter two main types of electricity. First up is static electricity. This is caused by friction. Think about shuffling your socks on a carpet in the winter, or giant storm clouds crashing together up in the sky. It builds up this huge amount of stored energy, and then bam! It releases in one sudden massive discharge, like a lightning bolt. On the flip side, we have current electricity, which is a steady, harnessed flow. And this is key. We absolutely do not want our homes relying on a wild, unpredictable discharge. Imagine trying to read a book while your living room lamp blasts with the force of lightning and then instantly goes dark. Yeah, no thanks. We need that controlled, continuous current to keep our appliances humming safely until we decide to turn them off.
Section 3. Generating the electric flow. So, how do we actually create and harness this steady, usable current?
People have been trying to figure this out since the 1600s, but we had a few major game changers. Back in 1832, Michael Faraday makes his huge discovery. If you move an electrical conductor inside a magnetic field, you create an electrical current. Magnets plus movement equals current. Fast forward to 1879, Thomas Edison rolls out the first long-lasting direct current, or DC, incandescent light bulb. But it was in the late 1800s that Nikola Tesla stepped up and pioneered alternating current, or AC electricity. Tesla's AC power was a real game changer because it made it way cheaper to shoot energy across long distances, which meant indoor lighting and factory machines could finally become an everyday reality. These folks figured out exactly how to tame an invisible force.
So how does Faraday's discovery play out today? Well, it's all about turbines. The heart of pretty much any power plant is a giant turbine that rotates massive coils of wire between huge magnets to create what engineers call electromagnetic induction. And here's the wild part. Whether that plant burns coal, natural gas, uses nuclear energy, or catches the wind and sun, the basic mechanical goal is exactly the same. They all exist just to spin those giant turbines and push those electrons into a steady, reliable flow.
Section 4. The science of circuits. Let's get into the main event and see exactly how we direct this flow of electrons. Did you know the word circuit actually comes from the word circle? It makes perfect sense, because a circuit requires a completely unbroken path for electrons to flow out of the power source, do their work, and travel all the way back to where they started. You really have to keep that circle analogy in your head, because if there isn't a complete continuous loop back to the source, the electricity literally cannot flow. It's all or nothing.
Now, to keep that flow safely on its circular path, we use two very different types of materials. First, we have conductors, like metal and copper. These guys transmit electrons incredibly well. They're basically the high-speed highway for our electricity. But we also absolutely need insulators, like rubber and glass, which block that electron flow. Think about line workers up on power poles. They're wearing those massive, thick rubber gloves for a reason, right? The copper wire conducts the dangerous energy, but the rubber insulator stops it dead in its tracks, so the human doesn't accidentally become part of the circuit.
As that electricity is safely cruising around its giant circle, we can step in and harness it.
We drop things like outlets, motors, switches, and all our everyday appliances right into the path of that flow. Think about a simple bedside lamp. The cord actually has a paired wire with 2 prongs on the plug. That whole setup is specifically designed to pull electrons in through one prong, push them up to light the bulb, and send them right back out the other prong to complete the loop.
It gets even simpler when we look at a basic wall switch. Here's the core idea. When you flip a light switch down to the off position, you are physically breaking the circle. You're literally creating a tiny mechanical gap in the conductor. That gap instantly stops the electron flow and bam, the light's cut out. Flipping it on bridges that gap, reconnects the metal, and finishes the circle so the electrons can rush through once again. It is such a simple mechanism, but absolutely profound in what it lets us do.
Section 5. The giant electric grid. Let's zoom way out from the switches in your house to the entire national setup.
The journey these electrons take is just staggering. Step 1, electricity is generated at the power plant turbines. Step 2, it gets pushed onto high voltage lines. You know those towering, massive wire structures along the highway carrying hundreds of thousands of volts? That's them. Step 3, it hits a substation where it's stepped down to usually under 10,000 volts. Step 4, it travels to transformers, those metal cylinders you see on telephone poles near your street. And finally, step 5, it flows straight into your home outlets. This means the exact same electricity that started miles away at a power plant is what's currently flowing out of your wall. The whole grid is basically one giant interconnected circle.
Section 6. Powering our daily lives. Let's talk about what this invisible force actually means for us as humans.
Take a second and think about life just 100 years ago. Before electricity was a common secondary energy source in our homes, we had to rely on candles and literal whale oil just to see at night. We used actual blocks of ice in iceboxes to keep food from spoiling, and we burned wood and coal in stoves just to stay warm. It was messy, it was a ton of work, and it was so much less efficient. There was no popping a meal in the microwave or chilling in front of a screen. Harnessing electricity completely revolutionized the human experience. It laid the foundation for the safe, thriving communities we live in today.
We really do take it for granted, don't we? We treat it just like the air we breathe or the water from the tap. But the next time you flip a switch in your house, I want you to ask yourself, what would your life look like if the electrons suddenly stopped flowing? What if that great circle just broke? I'm going to leave you with that thought, and I really hope you can now appreciate the incredible science circling behind the walls of your home every single day. Thanks for joining me on this explainer, and never stop learning.